Alright, hello CS11. This is lecture 18. This is the start of the last arc of CS11. So lecture 18 is about complete search. So for this last arc of CS11, yung main practice sets are going to be, aside from 10 and 11, practice set 9. So yeah, those three are your main at least practice sets for this third and final arc. Okay, so to motivate this lecture, let's start with this problem over here. So we have a binary string. By binary string, what we mean by that is it's just a bunch of zeros and ones. So something like this is a binary string. So what we want is we can perform this operation here, choose some substring or some continuous part of this string, then flip it once. So we want to flip all of the bits inside whatever substring we choose. So if we choose this 101 over here, the resulting string will become 010. So each bit here flips to the opposite bit. So the question is, if we choose the right substring, what is the smallest number of ones that we end up with? So here, if we chose this substring 101, we ended up with this is 1, 2, 3, and 4 ones in the resulting string. So the question is 4 the best that we can do? So we want to solve this problem over here. Alright, so if you were to write that as a function, we would want something like this to happen. So if we're given this series of ones and zeros, then this function should give us the integer form. So how do we actually solve this example over here? Okay, so well, let's first go through a few ideas. So first things first, our goal is to minimize the number of ones. So in that case, one thing we can do is, what if we get rid of the longest segment that has ones? So for example, here, let's say I have 0, then a bunch of ones, then 0. Let's say I have this string over here. So if I try to apply this rule for this string over here, we would end up flipping this first segment of ones. So this would become 0, then 0, 0, 0, then the rest stays the same. So this would end up with 2 ones. So at first glance, this does look optimal for the problem that we want to solve. So if we try to get rid of the longest series of ones, we will get a lot fewer ones than the original string. But the question is this the right idea? So as it turns out, it's not. So here, what we have is this string over here. So if we apply the idea we just went over, getting rid of the longest string of ones, then what we would get rid of is this middle part over here. So these 6 ones over here. So this would become, this is now 0, 0, 0, then another 3 zeros. So for this, if we apply the rule here, the rule over here, we would end up with 10 remaining ones. But as it turns out, for this example, the optimal flip is actually getting or flipping the entire string. So if we flip the entire string here, this is going to end up as a bunch of zeros, plus 1, plus 0 times 6, plus 1, plus 0 times 5. So this string, if we flip the entire thing, that would give us this. And here, there are only 2 ones left. So as it turns out, this rule is not the right rule for all possible cases. Okay, so if that doesn't work, then what does? So what idea will make us solve this problem correctly. So another thing we can try is, well, based on this example here, you can see that there are a bunch of lonely zeros. So here, there's a zero that's alone. Then what we're going to try to do is flip it along with everything beside it. So let's say for this zero, we're going to flip this, all of this. And for this zero, we're going to flip all of this. So as it turns out, even if we do that, if we do what I just mentioned for this particular string, flipping this is going to result in 5 zeros, then 1, then 6 zeros, then the rest of the string here. Then if we still count the second zero as lonely, then if we try to flip everything around it, so let's say we try to flip the surrounding characters around 0. So this is 0, 1, then a bunch of 1s, then a bunch of zeros. So if we flip this part, then this part, that's going to make us end up at this string over here, which at first glance is already much worse than yung optimal solution over here. So this idea is also wrong. So what else can we try? What if we start at a1, then we have this additional rule over here, while yung balance between zeros and ones is good for whatever definition we have for that, we're going to keep extending the part that we flip. So let's say here, for this example, we see a 1, and we see a bunch of additional 1s over here. We want to minimize the number of 1s at the end, so what we would want is to flip as many of these 1s as possible. So starting here, we would look through these 1s, so we see a 0, and even though we see a 0, yung balance between the 1s we've seen so far and the 0 that we've seen, there are a lot more 1s than zeros. So we could say that we should still keep going on even if we see a 0 over here. So if we keep doing that, we're going to go all the way here. Then next we see another 0. So all of these 1s, there are 11 1s and 2 zeros, and that balance is still kind of good. So you might think that, okay, let's continue. So let's keep going, then you eventually reach the end over here. So that would make you indeed flip the entire string. So is this idea actually correct? Start at a1, then just keep flipping as long as there are more 1s or a lot more 1s than zeros. So the first thing we have to go over is, what is this good in the first place? We have to come up with something exact so that we can actually write a program that does exactly what we want for us. So what is this good thing in the first place? So one heuristic is yung number of zeros, yun nga, that's less than or equal than the number of ones. So here, the single zero is definitely a lot less than all of the number of all of the ones before it. So that's one thing we could try using. But as there will be cases where this is eventually going to fail. So let's say you have something like this. Something like this. Here we have 4 zeros and 5 ones. So if you follow this heuristic over here, even if there were 5 zeros over here, you would end up flipping this entire thing. So let's say we have this. So if we do that, and we flip this is now 0, 0, 0, 0, 0, 5 ones, then the last 5 ones. And this is definitely worse than if you just flipped the entire thing instead. So this, then ones, then zeros. So this is a better solution than this. So our heuristic here still doesn't work. So when you encounter a wrong answer verdict, for example on OJ, then you might start thinking about, is your implementation in Python, is Is there something wrong with that implementation? Or is the idea itself wrong in the first place? Okay, so for this example, we can see that yung idea itself is wrong. So if you start here, then as I mentioned, if you encounter a bunch of zeros, your solution isn't going to work since it's also going to flip these zeros over here. So what if we try to repeat this procedure multiple times? So start here, then repeat or keep flipping until the balance becomes bad. Then you do that again at some other part in the string, then so on and so forth. Well, that might also be bad. So this is one example. Let's say you start here, then you, depending on your definition of balance, you will probably go through most of this string over here. So there will be cases, there will always be cases for this particular idea where no matter what kind of heuristic you try to come up with, for example this heuristic over here, you are going to reach a case where that heuristic will not work. So what do we do in that case? Well, we could try to build on top of that strategy, this strategy here. So we could build on top of that. So in some sense, we're trying to patch this incorrect solution over here. So as we keep patching, there's a chance that that patch solution also breaks. Then if you try to patch that solution again, there's a chance that there's a case that still makes that solution fail, then so on and so forth. So how are you going to know if that series of patching your previous solutions is ever going to end? So is there a cleaner way to do all of this? Instead of failing, then trying again, then failing again, then trying again, then so on, is there a more straightforward way to get around all of this? Okay, so in addition to that, whenever you try to patch your previous solution, naturally, the way you implement that solution is going to become harder. So since it becomes harder, it's also going to be easier to run into bugs. So for example here, this idea, yung keeping track of the balance between zeros and ones, this is much harder to implement than yung very first idea natin. And that was flipping the longest series of ones. That's a lot more straightforward than keeping track of some arbitrary balance. So as it gets harder, it also gets harder to debug. So what should we actually do? Is there a completely different approach that we can try out? So in fact, there is. So that is going to be the main takeaway from this lecture. So yung correct solution for this problem over here is, well, since we're only going to do the operation exactly once, we're going to flip some substring of the string exactly once, then why not just try everything? So literally what I mean by that is this is the function we want to implement. Then the way we implement that over here is we try all possible flips. So this function here, this returns the string if we flip it from I to j. And I and j is all possible, represents the indices of all possible substrings of S. So this is index pairs, this function here, and this is the main function. So this is literally just flipping the necessary bits. Okay, so in that case, this tries out all possible substrings that you can flip. So it tries out this, for example, then this second character, third character, then all of the length 2 substrings, then all of the length 3 substrings, and so on. So eventually, it is going to come across yung best case scenario. So for example here, for this string, it's eventually going to try flipping this entire string. And because of that, it will get the right answer over here, inside this function, inside this part over here. So that is what brute force is. If you have a problem, try to see if you can try all possible ways to do what the problem asks you to do. So if you're trying to flip some substring, try to do all possible flips. So the main reason why we want to encourage brute force is that, well, brute force is always correct. No matter what test case you come up with, whatever input you give to the function, it's always going to give you the right output, well, assuming you implement the brute force correctly. But as you can see here, implementing that brute force solution is usually very straightforward. You literally just do what the problem asks you to do. Okay, so since the idea behind brute force is that don't be clever, so this might not be good advice in general, but at least for CS11, for solving tricky problems like these, it's always a good idea to try to find something that works before trying to find something that's clever. So another reason is that, well, computers are very fast. Even if your string is a bit long, your computer can easily go through all of the substrings of that string. So your computer is capable of performing a lot of operations at once. So to show that, let me just run this loop over here. Every second, all of these lines here kind of represent a single operation that your computer can do. So as you can see, your computer can do lots and lots of operations in each second. So in that case, there's nothing stopping us from, well, trying all possibilities over here, especially if the number of those possibilities is around the numbers you see over here. So brute force for small inputs usually runs very fast, and that's why it's one very viable way of solving different kinds of problems. Okay, so yeah, let your computer do all of the hard work. Okay, so let's look at another example. So you have a sequence and you have a number. So you want to count the number of subsequences. Now a subsequence, let's say you have a sequence like this. A subsequence is not necessarily consecutive, so yung 1 and 3, this still counts as a subsequence of this tuple over here. So we want to find all of the subsequences. We want to find the largest sum that is less than or equal to m. So how do we solve this problem over here? Okay, for this example, here yung largest sum that's less than or equal to 16 is 15 because of the 8 and the 7 over here. 8 plus 7 is 15. So how do we solve this problem for any sequence that we get? Okay, so one thing we might try is, well, be greedy. So we might want to start with the first element, then let's try it with this example here. So we have this sequence, then our target is 16. We want sums that are less than or equal to 16. So what we might want to try is get the first element first, so 10. Then we look at the next element, is 10 plus 8 less than or equal to 16? No, so we skip 8. So we move on to 5. Is 10 plus 5 less than or equal to 16? Yes, so we include 5 as well. So we keep doing this. Is 10 plus 5 plus 7 less than or equal to 16? No, so we skip that as well. Then of course we also skip 10. So we end up with 10 plus 5, which is yung right answer over here. So you might already see how this can go wrong. For example, if I made this 3 instead, so what I would do in my greedy solution would be to get 10, skip 8, then get 3 since 13 is less than or equal to 16, skip 7 since 13 plus 7 is already beyond 16, and skip 10 as well. So if we did this greedy solution, we would end up with 13, not 15. Still from the 8 plus 7 over here. So for this case, yung greedy solution is also wrong. So what do we do instead? Again, the point is brute force. If we want the largest sum that's less than or equal to m among all subsequences, then there's nothing stopping us from just trying all possible subsequences. So for each subsequence in this sequence, we check its sum. If the sum is less than or equal to m, then that's one of the numbers that we consider. So we just want the largest sum among all of those sums that are less than or equal to m. So that's what this line over here does. So for each subsequent sum in this sequence, if that sum is less than or equal to m, we just get the maximum out of all of them. So in one line over here, we've already solved the problem using brute force. Okay, so we still have to implement subsequent sums. This is, again, wishful thinking. We're assuming that we already have this function for us, which we don't yet, but if we pretend that we do, then implementing the main function that we want is actually really straightforward. It's just this single line over here. So in that case, subsequent sums. So in turn, this function, we can write that like this. So for each subsequence in the original sequence, we just get the sum of that subsequence. So this would be one way to implement this function here. So this is wishful thinking yet again. What we want this time is to get the subsequences of a particular sequence. Okay, so now what we've done here is we've reduced the problem of getting the max subsequent sum to getting the subsequences of some particular sequence. Okay, so we just want to enumerate all of the subsequences here. Okay, so we'll look at different ways to do that. So our problem is now this. It's a lot more straightforward than the original problem. Okay, so this is what that would look like for ABC. These are all of its subsequences. So yung length 1, ABC. Length 2 is AB, AC, and BC. Then, of course, you have ABC itself. Okay, so the first solution that we're going to look at is a recursive solution. So when it comes to a subsequence, let's say for ABC, or AB, for a smaller example, for AB, yung subsequences are A, B, the empty string, and AB. So these four over here. So in that case, if you notice, each of these subsequences here, they either contain the first character of the string or they don't. So we can group all of these into A and AB as well as B and the empty string. So that's what this statement is saying over here. And because of that, we can actually write the subsequences function like this. So what you're going to do is remember from the first arc, if we want to do recursion on a sequence, we split it between the first element and the rest of the elements here. So here, this is all of the subsequences from the rest of the sequence that do not contain the first element. So this is the same for loop, but here what we're doing is we're attaching the first element to the front of whatever subsequence we get from this recursive call. So what's happening here is, for this first group, A and AB, you're basically writing this as A plus the empty string and A plus the string B. And for the second one, this is just the empty string plus the empty string as well as b. So yung empty string over here, you either add a to that or you don't add a to that. Same thing for b over here. This is the rest of the string. You either add a to that or you don't add a to that. So that's what this function is doing over here. Okay, so that's one solution. Another solution is, well, since we're calling the very same thing over here, we can just call it once. So we can set it to, or we can combine the two for loops over here, and inside a single iteration we yield twice, one for the element without the first, one for the subsequence without the first element, for example this empty string over here, then one yield for the one with the first element, so that would correspond to this over here. So this would be another solution. We're just technically cleaning up this first solution over here. Okay, so what other things can we try? So this over here, this only works if we can index this sequence here. If it's a generator, remember we cannot use indexing for generators. So x for x in 1, 2, 3. If we tried to access this by indexing, we would get an error. So how do we handle this for generators? Well, that's pretty straightforward. Just convert it to a tuple first. So this is a function, the subsequences function, then we're delegating it to a separate function, underscore subsequences. Then here, what we pass into this function is the same sequence, but we convert it to a tuple first. And this underscore subsequences is just exactly the same as yung second solution over here. So we convert first before we do all of the stuff over here. So yeah, this will now also work with generators. Okay, so that works now, even for generators. But there are some other minor problems that we will run into because of that. So first things first, because this sequence over here, this is now a tuple because we do the conversion over here. Remember that whenever we slice tuples, so 1, 2, 3, if we slice this from 1 onwards, we get an entirely new tuple. This is completely separate from this tuple over here. Okay, so this is wasteful in terms of memory, as we went over in one of the previous lectures. So in that case, can we try to do index-based recursion instead? So instead of doing these wasteful operations on tuples, what if we only keep track of yung index? So what would that look like? How would we transform this function over here? So for that one, that would look something like this. Remember, for index-based recursion, what we're basically doing here is we add an extra parameter to represent our index. Then in our new function, what this is now, since we're keeping track of the index, we no longer have to explicitly slice out some part of the sequence. So what's happening here is, if this I, this index tracker over here, if this goes beyond the valid indices for the sequence, then there's nothing else to generate. Otherwise, we continue generating over here. So here we increment the current index, then this is where we put the stuff from before. So that's the same thing as this over here, except this 0 is now I, since the way we defined this recursive function is all of the subsequences from index I onwards. So yeah, that's the index-based recursion. Okay, so this sequence is now the very same sequence all throughout this function. Here, 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 and here. So does this now solve all of our problems? So one optimization that we can make is, well, if you notice here, since all of these refer to the same sequence anyway, this sequence the sequences here as well as yung sequence over here. These technically refer to the same sequence. So what we can do is we take all of this, then we just shove all of that into this original function here. So that's what this would become. So this is from the original subsequences function, then this is what we shoved into, or this is what we put into that function. So since the sequence remains the same throughout this inner function, we no longer have to explicitly put sequence as a parameter in this inner function. So instead of writing subsequences, then sequence, then I, we just write subsequences, then I. We no longer need the first parameter. Same thing for this recursive call over here. Okay, so we still do the conversion, of course, since we still need to handle generators as always. So yeah, this is now a lot cleaner than our very first solution, but we still can do better. So how can we do better? Let's look at some additional ideas. So first things first is, although we no longer directly manipulate the sequence over here, we still use it whenever we're making new tuples. So this new tuple is completely separate from the sequence and S over here. So that part is still kind of wasteful in terms of memory. So what can we do for that? Well, if the fact that we're using tuples is the bottleneck here, what we can think of is, what if we try something that's not a tuple? And for that, what comes to mind first is the counterpart, the mutable counterpart of tuples. And that is, of course, the list. So before that, let's try to change this a bit first in preparation for what we're about to do later. So here, what we're basically doing here is we're turning this to a cumulative recursion. So we're building up some partial result over here. Then we keep track of that partial result in the recursive calls. So that's this, and that's these two recursive calls over here. So notice that we've actually gone one step backwards. We now have the two for loops yet again. So also, it doesn't really solve the issue that we had of splatting some tuple into a new tuple. That still happens in this part over here. Okay, so yeah, we have to recurse twice again here. So what do we do in that case? So first, let's do a bit of cleanup first. We can turn this, remember, if we're just iterating over some sequence, then what we're doing in each iteration is just a single yield. We can rewrite all of this as yield from. So yield from this sequence, then yield from this other sequence. So this is just a bit of cleanup. Nothing has changed. We still have this issue as well as the two recursive calls over here. Okay, so the reason we turned this into a cumulative recursion, the reason why we have this partial thing over here, is because of what we're about to do. So if we now use a list instead of a tuple, what will now happen is, since this is mutable, we can make this part and this part work on the same list over here. This makes a new tuple, or this is the partial tuple, but this is a completely separate tuple. If you want those two entities to remain the same, although they might have slightly different elements, that is what lists are perfect for. So here we have this is the first recursive call, then here we're appending yung sequence I. That's essentially what's happening here in this version when we're putting sequence I at the end of this tuple here. So we append it, then we make a recursive call. This part over here, this is meant to do the same thing as this line over here. We're making a recursive call where we update the partial result. And after this, what we do is, since there are still other recursive calls going on, if we append somewhere here, we have to undo that thing for the next recursive call. So if we append here, we have to pop it at the end over here. So append, then pop. So this will now, this essentially does the same thing as this. It's the same idea. But now, since we're using the same container throughout all of the recursive calls, this is actually much nicer or much more efficient in terms of memory usage. Okay, so again, dot append instead of making an entirely new tuple or list. And we have the pop, since if we don't pop, for later recursive calls, this part where we appended sequence I will still stay. So we won't get the right result. So we have to pop, and we also have to yield tuple of partial. So if you look over here, this part here, since partial is a list, and well, if we just yielded partial, what would happen is we're yielding the exact same reference to a list whenever we yield. So all of the lists that we end up yielding will be the same list. So that's as if I had x is equal to this empty list, then y is equal to x, then I just yielded x, then yielded y. Define f, yield x, yield y. Something like this. This x and this y, as we went over in one of the first imperative lectures, these refer to the same list. So that's how you have to convert it to something else first, in order to avoid making them refer to the same thing. Since we append and pop over here, that will naturally change what this partial result is throughout all of these recursive calls. So we have to convert it first before yielding. Okay, so finally, since all of this partial stuff, you're essentially just using it as the same variable. You're not doing anything directly to the variable itself. What you can do is extract all of these, just like how we extracted sequence a while ago from this inner function. So we can extract all of the partial stuff outside over here. So our inner function, again, now has a single argument for I, yung starting index. And yeah, this is now what the function is going to look like. So all of this is still the same thing as the previous version. The only thing that's changed is that our partial result is now stored outside the inner function. So this is now our solution to the subsequences problem. If we run this function on a sequence, we will get all of the subsequences of that sequence. Okay, so this is actually what we call a backtracking function. Remember from the first arc, we went over yung coin denominations problem. That was the first instance where we saw what we call backtracking. So if you remember how it went over yung denominations, yung 3, 5, 7 for example, and if you want to check whether you can make some amount out of these denominations, for example, I think it was 48 or something, you would try 48, you would make a recursive call to 48 minus 3, then 48 minus 3 minus 3, and if that doesn't work, you pop that minus 3, then you try minus 5 instead, then so on and so forth. That backtracking idea is the same thing as what's happening here. You explore this possibility whenever you append, then to backtrack, you pop at the end over here. So all of this involves lists and yields, so this is now an imperative backtracking function. The one we saw from a while back was just recursive or declarative backtracking. This is now imperative backtracking. Okay, so that was a lot of ways to get the subsequences. But now that we have all of those ways, we can now actually solve yung original problem. So remember, yung original problem was getting the max sum less than or equal to m out of all subsequences. So now that we have this function over here, we can now solve that original problem. And actually, since this is such a general function, you have a sequence, get all of its subsequences, we can also solve many other kinds of problems that involve subsequences. So for example, if I have this problem over here, how many subsequences have a sum that is prime? So let's say define num subsequences with prime sum. Again, brute force, try all possibilities. So what we literally do over here is return, I guess, the length. Then what we have here is subsequence for subsequence in all subsequences of the sequence if the sum of that subsequence is prime. So we can make an additional function over here for is prime. Then there, that's already a solution to this problem over here, since we have this subsequences function already. This is subsequences of the sequence. And for is prime, we can just implement that separately. But the point is, since we have this function, it's now very easy to solve this separate problem. Okay, so brute force allows us to build useful functions like these that also allow us to solve many other kinds of similar problems. Okay, so because of that, what we really need in order to solve problems using brute force is to be able to come up with or build tools that allow us to enumerate different kinds of stuff. So for example, subsequences, which we went over in this lecture. There's also permutations and combinations, which you can look up if you want. And yeah, if you know how to generate all of these, then it's very straightforward to come up with brute force solutions. Just use the functions you have for these, then process that data in some way, just like what we do here. Okay, so that's the nice thing about brute force. Of course, it's not all nice. There are some not so nice things about brute force, and one of them is shown by this video over here. So if you have the time, do go over this video. It's a very fun watch. But the point of this video is that brute force, although it's correct, it's not always that fast. If your input gets big enough, brute force can become very slow. So it's correct if we want to wait. So what will come into here is the fact that although computers are fast, they are not infinitely fast. So they're computers at the end of the day. They should obey the laws of physics. These are physical objects, so they have their own limitations. So brute force comes at a price, and that price is what we call inefficiency. So before we go into how brute force is actually inefficient, we have to first answer the question, what does it mean to be efficient in the first place? So how do we know if some function or some program is actually efficient? That is going to be what the next lecture is for. So in the next lecture, we will go over how to measure efficiency. Okay, so that is what we'll have in lecture 19. Yeah, so that's going to be it for this lecture. This is the corresponding reading for lecture 18. But yeah, that was complete search. So in lecture 19, we're going to talk about efficiency and how complete search can be inefficient. So if it's inefficient, we're going to need to come up with ways, or we're going to need to come up with efficient solutions to problems. And that is going to be what some of the next few lectures are going to be for. So before all of that, we will talk about efficiency first in lecture 19. So yeah, that's going to be the end for this lecture. Thank you for watching.